All right, so let's look at some examples today for lesson number 8. We're looking at friction. So let's see what the question reads as. So we have a man is pulling a block with a mass of 6.2 kilograms across a horizontal surface, and it accelerates the block at a rate of 0.5 meters per second square. The coefficient of kinetic friction between the block and the surface is 0.24, and they're asking us what is the magnitude of the force which the man pulls. So this is a very simple question. There's someone pulling on a block, the block happens to have friction, and they're asking you, hey, what is the force that this person's pulling such that there's this much acceleration, 0.5 meters per second square. So the first step that we should try to do, draw a situation. So we have the system diagram. So let's just draw a surface, horizontal surface. We have a block and a random person. Now, what is this random person doing? They're pulling on the block. So in this case, we're going to assume that the direction is to the right. So again, they don't tell us that, but we can make that assumption. So we can conclude, or assume, that the acceleration is to the right with a rate of 0.5 meters per second square. All right, so once you have a system diagram, we have a person pulling on a block to the right across the horizontal surface. We want to draw the forces that are acting on the block because that's our object of interest right now. So right away, the one force we can't run away from, the force of gravity. So Fg, the block is on the surface, so we have the normal force which is perpendicular to the surface, Fn. And because we assume that the person's pulling to the right, so the force acting on the block will also be to the right. So let's call this an applied force or pulling force. It doesn't matter what you call it. So applied force is whenever you make contact with a surface, usually from a person. And because there is friction, friction wants to oppose that direction of motion. Or in this case, because it is actually moving, it opposes the direction of the moving object. So the friction will be to the left. And because the object is making contact with the surface at all times, we could be more specific and call this Fk for kinetic friction. So we have a system diagram, the object's moving to the right, we identify the forces. So now we just need to identify our net force. And the net force is just the sum of all the forces. So we're going to add up all the forces, the normal force, gravitational, frictional, kinetic, because again the object's making constant contact, and our applied force. Alright, so once you have that, we're going to break this down into its components. So we're going to go along the x components and along the y components. So we're going to call this F net x. Alright, so now we're going to look at each of these forces and we're going to pick apart the x components. So if you look, we only have two forces along the x, but we need to stick to the convention that if it's pointing to the right, it's positive. If it points to the left, take it as negative. So that means the applied force is positive, and our kinetic frictional force is negative. So that's where the positive and the negative come from. Okay, but in this question, the object is actually accelerating. So we know from Newton's second law, that the net force is going to equal to mass times acceleration. So we can change the F net along the x to be ma x, so the acceleration along the x component. And again, we assume it's going to the right, so that's why we took this to be positive. The other side remains unchanged. And since the question is asking us to find the applied force, all we need to do is just isolate for the applied force from this equation. So our applied force equals to mass times acceleration along the x plus kinetic friction. So now if you look at what was given to us, we have the rate of acceleration. 0.5, we could substitute that in. The mass of the object, we could substitute that in. But they didn't give us the frictional force. So we're kind of stuck. Well, we're not stuck, remember that. Whenever you have the x components, you're never stuck because you have the y components to complement them. So now we're going to repeat the process of resolving the vectors along the y. So f net y equals 2. Now we're looking at the y component. So here the normal force is pointing up, positive, force of gravity down, negative. Normal force minus gravitational force. And we apply similar analysis, so from the second law, but this object is not moving up or down. So in other words, there's no vertical motion. So the acceleration along the y component will be 0. So since no vertical motion, what does that mean? F net y equals to 0. With that conclusion, that leaves us with 0 equals to the force normal minus the force of gravity, which we can conclude that the normal force equals to the force of gravity. Well, we have an equation for the force of gravity. That's just calculated by g. And g, we should know, is 9.8 meters per second squared. Mass we have, so we could calculate the normal force. So here we have two equations. And again, what was the point of this? We were trying to find the applied force. But the y component doesn't have anything that we need. So we need to borrow yet from another equation. So we got to borrow from the relationship of kinetic frictional force. So there's another formula that we looked at before. Kinetic friction equals to the coefficient of kinetic friction times the normal force. So that equation comes out of nowhere, but that we got from our graphs. So we have this relationship. So we can take advantage of this equation, just like we did for the force of gravity. Nobody told us to use mg, but we have to know it. Same thing with this one. We have to know this relationship, so we can substitute it into this equation. So what would that give us? F apply equals to max. So instead of kinetic friction, we use the relationship with the coefficient times the normal force. But now you're like, oh, that's fantastic, because the normal force we already found from the y component, so we can substitute another equation into here. So let's see what we end up with. Maybe I'll erase this here. Okay, so we end up with the applied force equals mass times acceleration along the x plus mu k. The normal force, we got it from equation 2, equals to the force of gravity, which is just mg. So at this point, we just need to replace the values and put it into our calculator. So let's see, let's try that out. 6.2, 0.5 plus 0.24, 6.2. All right, so we get a value for the applied force to be equal to 17.7 newtons. All right, so that's example 1, pulling a block.